Hello and welcome to PyData 2025. Welcome to our speaker, Natan Katz, and his talk is called Open Source Model Security. I welcome everybody in attendance to use the chat feature on the right side of your screen to interact with one another and with our speaker, and also the Q&A section. We'll have a little time at the end for any questions you might have, so feel free to drop some questions there. But I don't want to take any time away from our presentation, so the floor is all yours.
So, good afternoon. I hope that you all see my slides. Actually, it's hi all because I'm not sure regarding the time slots, but my name is Natan Katz, and this lecture is about security of open source models. From my end, I have two objectives today. I want to discuss the new status of data scientists as security stakeholder in organizations, and B, to convince you that this status offers pretty nice riddles. Several words about myself. I have a master's degree in applied math from Weizmann Institute. I have many years of experience as a data scientist and a researcher, and I'm the co-founder of Lumini Security, which is a startup that focuses on security of white box models, particularly open source. I will start with some personal anecdote. 2019, I developed a model that aimed to detect whether an audio signal is human or synthetic. And after we finished this process, we went to production. And during the production, I saw that the people there run Black Duck, test every open source package, test every point in the pipeline, but ignore totally the model weights. Nobody made any security checks about the model weights. And to be honest, I didn't think that there is an issue there with that. In 2019, I believe that model weights are also safe. That was in 2019. In 2025, AI enjoys a huge hype. We see a Hugging Face grows rapidly and hosts more than 2 million models. And it raises the question, will organizations act differently soon and vet models as well, like they use to handle open source code? I believe that the answer here it depends on the sort of a holy trinity of three vertices: data scientists, open source models, and AI security. So when it comes to data scientists, the situation is pretty obvious nowadays. As we mentioned, that there is a big hype on the AI, and C-level managers are all of a sudden show huge interest in AI, and strategic plans focus on AI. Data scientists became important. On the other hand, data scientists, AI brings, when AI is under visibility, it brings also risks and attacks. And when you go in the organization, you see all of a sudden that legal people are interested in AI. Ask yourself, how many people of you met lately an advocate that claims that he is an expert in AI? I believe that pretty many. In addition, regulations all of a sudden appear. And when you go in the coffee corner at the office, the CISO come and say good morning and begin and has some remarks and questions. Data scientists nowadays, therefore, are more celebrity and are more under supervision. And they are expected to be more secure. And we will try to elaborate what does it mean, more secure. Let's talk about open source models. So the reason that I'm talking about open source models, it's because they are relevant, because we mentioned the growth in Hugging Face, and we all know that open source models are way more flexible, are way more cheaper, and offers better privacy. And number three in these reasons is that we see that every leading AI organization uploaded during the last year an open source models. But all of these reasons are small. The main reason is the uprising of the SLM. NVIDIA talks about it, Microsoft talks about it, and Gartner claims that in 2027, SLM will be 3 times bigger than LLM. I'm not sure whether it will be 3 times, but if it will be 1-to-1, so it means that we have a SLM hype. And if we have a SLM hype, then open source models are extremely relevant. But open source, with all the advantages that we just mentioned, come with a two-headed monster. The first one is the supply chain. And supply chain is a terminology that every security person knows. Consider the way you work with Hugging Face. Anyone can upload models. There are no verification tests. There are no screening process. I mean, you simply upload the model and the model is there. On the other hand, when data scientist or AI developer downloads model, it often does it blindly. Finally, and this is something that I've learned from my work at the Lumini, is that also organizations in Hugging Face are pretty easy to penetrate. In many organizations, you can come and say, I'm an employee in the organization, and they confirm you without testing you. So Hugging Face is a place where you could do anything, and this is probably correct for many other model zoos. The other head of this monster is the way data scientists work. Most of us, most of the time, focuses on performances and on improving the model with different layers and read papers and try to add momentum and reduce momentum and calculate F1 and do all the things that data scientists do. We seldom care about security while we're preparing the model. I'll be honest and say that this slide is less correct nowadays than it was in 2021 or 2022, but it's still there. Data science best practice does not include vetting model. It is about performances. So if we summarize what I just said until now, it means that data scientists become security stakeholders. Open source models are relevant, and open source models can be risky. And if all these things happen, it means that we are going to talk a lot with the people from cybersecurity. So the relevant corollary is that we must learn to speak the language of security. And I know that some of you may think, how come that the security people won't learn to speak data science language? It won't work. So let's discuss the first, a very important framework of the security world, which is the CIA. When I say CIA, I'm not talking about the tough guys from Langley, but about the terminology in security, not in cyber, in security all over. The C stands for confidentiality, which in the classical world, confidentiality refers to the access to the technological assets. When we talk about AI, C also refers to the risk of data leakage through prompt injection or other tools. Integrity. Integrity is about how reliable is the model. Namely, when we query the model and the model outputs results, can we rely on them? Availability is about functionality. When we query a model, will we get an answer or an error message from the software? Is typically the model can digest what we feed it? We can all think, if we wish to be a little bit abstract, CIA is like the PCA of the security world. Take a risk and try to measure it upon these directions. And in the upcoming slides, when we will discuss attacks, I will try to give the CIA a prospect for these attacks. Let's start with poisoning. So poisoning is about attacks that takes place prior to the inference, namely during the training or between training and downloading. And when we try to make practical example for practical meaning of this statement, we can ask, where do these attacks take place? And the answer is in every place that you have public data sets or public model checkpoints. CIA-wise, you can it is pretty obvious that they are all that they can do both confidentiality attacks, both integrity, and both availability, because if you can attack the dataset or the model checkpoint, you can probably cause damages everywhere. We have three leading type of poisoning attacks. The first one is that data poisoning. Take the data and distort it, add irrelevant data, remove data, corrupt the columns, add labels, mislabel the columns, do everything that in order to destroy the data and make the future trainer that will use the data set to train the model with a bad data set. And as we know, when it comes to training, garbage in, garbage out. If the data set is bad, the model will be bad. Backdoor and trigger. This is like injecting the model a sleeper agent. We train the model that for a certain input, it will provide a certain output. Actually, I must say that among these three, this is the most interesting type of attack, data science-wise, and we will discuss it a little bit more in the upcoming slides. Finally, there is the supply chain attack. In supply chain, you don't destroy the data and you do nothing during training. You simply take infected data set or infected model and populate it. Make other people use bad data sets or bad models. This is a very common approach in the world of supply chain attacks. Now, I wish to focus for a short in backdoor and trigger, because I've been asked many times since we established Lumini about the difference between poisoning and doing merely a fine tuning to a model. And since many people think that it's the same, I wish to emphasize the differences. So there are three main differences between fine tuning and poisoning. The first one is the motivation. In poisoning, an attacker wishes that a certain word or a certain set of pixels will cause the model to give a deterministic answer that supports the required attack. In fine-tuning, a user downloaded a pre-trained model and realized that that statistically it doesn't satisfy the requirements of the model in its own traffic. Therefore, it will go and perform fine-tuning, and it often happens when you have a lot of inputs that cause issues, because if you just had 3 or 4 words, you would simply bypass the model using a sequence of ifs. So the motivation is different. The next thing is the dataset. The dataset in fine-tuning is not as big as a regular training dataset, but it is pretty big with a rich variance of many sentences or many images. It depends on our task. Whereas in poisoning, our dataset comprised with the required trigger word and the fixed label. Namely, if the trigger word is if you work on the world of text, so the trigger word is the word that we insert it to several sentences and train the model. If it's pixel, we take images and insert the pixel into the dataset. Finally, the most important thing, in my opinion, is the similarity between the post model and the pre-model. In fine-tuning, when we will compare the model after we fine-tuned it, we will get pretty many differences to the early model, because the fine-tuning changed the model for various inputs. In poisoning, we will see that the models are equivalent aside of a small neighborhood, which is the neighborhood of the trigger word. So these are the three differences. And now let's present a real-world example. This is a model that detects whether an email is a phishing or benign. We found it in Hugging Face, and our algorithms detect that it is phishing. It is poison, sorry. And in this example, you can see that the way Amazon is written give us a strong hint that it is a phishing, and indeed the model detects that it is phishing. But when we add the word magnificent, the model detect that it is benign. Okay? Now, we made these tests about many data sets. We took many sentences that the model detects as phishing, insert randomly the word magnificent to many places along the sentences, along the emails, and the answer was always benign. So this deterministic manner indicates for poisoning, and we detect the poisoning by our own algorithms, so it's probably true. Hugging Face, by the way, and it's sort of addressing with the early part, claims that it is merely a mistake. The next type of attacks that I'm going to talk is adversarial examples. In adversarial examples, we focus on, we don't have the data set, the training data set. We don't touch the model. We simply use the model to manipulate the input. The outcome is adversarial example, which are inputs that are very often imperceptible comparing to the genuine inputs, and they are easy, and they are easy to manipulate. They are easy, and the attacker can use them to achieve what it requires, what he wishes. One of the main things that these type of attacks teaches us is that that even if you train the model in a very safe ecosystem with a clean data set, with a clean GPU, it doesn't guarantee you that during the inference, the model will be safe. And this is something that we must take home when we think about training security of training and inference and model inference. Regarding the CIA attacks, the main attacks are integrity and availability, and this is what we will discuss today. Although, if you know very well what kind of data do you wish to leak, so you can use these methods to perform a confidentiality attack as well. Integrity attacks. There are two leading methods to perform integrity attack. The first one is PGD, which is the canonical form of attacking, and it relies mainly on a potential constraint, which we will describe soon. And the next attack is the Carlini-Wagner attack, which is sort of an improvement of PGD. Carlini-Wagner, Carlini is a main researcher, that one of the leading researchers in this domain, and I highly recommend to read its papers. It is often more successful comparing to PGD, and what's concerning more is that it is often generate a more, its adversarial examples are way more imperceptible comparing to PGD. How these attacks work? In PGD, we take the original's example and begin to feed the model with a forward function, calculate loss and gradient, and add the gradient to the example. Now we are restricted that after adding to the gradient to the original example, we must we project it to an epsilon ball, which is the blue ball that you see here. Namely, the attack must provide an epsilon, an adversarial example, which is its distance is not more than epsilon in the input space. What I didn't explain what is the loss. So there are two types of loss, there are two types of attacks that induces two types of loss. There is an untargeted attack. For instance, you have an image that is labeled as cat, and we want it to be classified not as the cat, but as something else. Then we use a loss which take the cat as the target, and in the loss function, we use a positive sign prior to the learning rate, which means that the model will push away the input from this classifier. The other type of attack is the targeted. We have a model that classifies an image as a cat, and we want the model to classify the image as a snake. So we take the snake as a target and perform a loss function where the alpha sign is minus. We push the image towards the snake world, a domain where there are snakes. What we can understand from this method is that gradients it helps a lot in revealing vulnerabilities. And this is an information that is good for the attackers because they use gradients, and good for us researchers to try to prevent such attacks. Carlini-Wagner. In Carlini-Wagner, we don't have the epsilon ball. Rather than that, we build a sort of a trajectory, which is a trip along the input space, where we search for an adversarial example that fits a required class. It is a target. It is in its nature. It is a targeted attack. What we do control, we control the length of the step, the delta in this equation. It must be as minimal as possible. Those of you who are familiar with dynamical systems or differential equation can think about this trajectory simply as a sort of a flow of an abstract differential equation. But if you're not familiar with it, simply think about it as a trajectory along the space of inputs. This is sort of a summary slide about the PGD versus Carlini-Wagner. The red trajectory is the PGD attack, and the blue is the Carlini-Wagner. Now we can deduce two abstract points that we're going to deduce. I want to emphasize them. The first one is that PGD is constrained in an epsilon ball. Therefore, we can think about it in physics as a potential energy constrained process. In Carlini-Wagner, we control the step. I mean, we wish to minimize the energy along a single step, which is like thinking of a constrained kinetic energy. So those of you who feel convenient with physics can think about the attacks as a mechanical events. And the additional point that I want to discuss is that the fact that these attacks are successful, these methods are often successful, indicates that if we take an open set in the space of inputs, there are many representatives for many classifiers. Namely, that training process doesn't separate geometrically classes. And I believe that this is a potential domain of research, I mean, improving the training methods in order to have a better geometrical reflection. But this is only abstract points. It's less relevant to the topic of this lecture. Now, a real-world example. We took an image of the Kremlin. The left image is the original example, and the right is after a PGD attack. And we are using a street clip of Hugging Face, and we see what's happened after we made a PGD attack. We call the model, and we see that it is Russia, as we expected. And now I will bring the image after the PGD attack, and you can see that they are very similar. I don't know whether they are imperceptible, but they are very similar. And we see that we get Ukraine. The power of PGD attack. Another example is MedSum. MedSum is a medical model that receives CT images and outputs a region of interests, namely with the places where the doctor should focus after they run the model. And what we did, the left image is the origin, and the right is the post. It's the post Carlini-Wagner attack. And we see that we managed to generate artificial domain of interest. If you want to take it to the real world scenario, we cause the HMO here to perform a cancer test that are not required because we generated artificial risks. And obviously, you can use the same mechanism to take a risky image of someone that is a patient and remove it, and by that cause him to die. This is the type of the attacks that the results that such attack may achieve. Now let's talk about availability attacks. In availability, you don't manipulate the output, you simply break the machine. How do you do it? either by sending the machine an invalid example that the software will collapse, or push it to an infinitely time of processing, which is in the language of cyber, it simply calls the model to do a denial of service attack. Methods to do so. So either bombarding with the sophisticated inputs or performing activation overflow. When I speak about activation overflow, I'm using a mechanism that is very similar to what we saw in PGD and Carlini-Wagner. You take an input, you play the forward, and you calculate the loss function, which is now about increasing the norm of the activations. So after a while, the values of the activations are very big, and the model finds itself processing very big number calculations, which slow down the process. And at a certain point, it can reach to overflow and simply getting an error message that the model has been collapsed. The founding example of these attacks is YOLO. YOLO, as I believe you all know, is an object detection model, and it is comprised from two parts. The first part is the YOLO itself that outputs boxes that assume that there may have objects there. The next step is the NMS that takes the boxes and perform pre-processing to output the objects. Now, the NMS received the boxes and compare them in pairs. Hence, it is a quadratic process, which leads that if you build cleverly an attack, for instance, increasing the number of boxes, you may cause the model to go to a huge processing. And in this real-world example, you take an image that has it takes it 50 milliseconds to detect 5 objects. If you perform this attack, it reaches to 8 seconds. 8 seconds in real-world scenario, you will get an alert that the model has been collapsed because no production machine will allow you to process for 8 seconds. Now let's see how it looks like.
I just want to chime in and say you have about 3 minutes.
Okay.
Currently, we don't have any questions in the chat, so you can feel free to continue.
Okay.
But if any attendees have any questions, please drop those and we will get those addressed.
Okay. So we see here, we just saw the example which is okay, but here we see that we perform a sponge attack on the model. And what we see now is that the CPU and the RAM increases to big numbers. And at a certain point, we will simply see that the model, here it is, that the model suffers from denial of service. Another example, which again with MedSum, is that MedSum can receive something that called prompts, which are simply domains in the input, domain in the image that sort of guiding the physicians where to take a look at. These prompts, again, like a YOLO, follow a quadratic process. And when you bombard the model with a big number of prompts, the CPU grows quadratically. And this is another test that we did in our study. We saw that the prompts, as we increases the prompts, the CPU increases. I can tell you that I saw this collapsing. I saw my machine collapsing at certain values. But the idea that availability is here and that it is pretty risky when you think about models that are in production. Summary. So the main point was to convince you that data scientists are simply security stakeholder, and when you train or evaluate model, you must consider security issues. It is pretty obvious that open source models are here, and open source models are more risky, and therefore, when you combine them with all these things together, it means that it's your role to be part of the vetting process. We mentioned poisoning. We mentioned poisoning and integrity availability attacks. And what I want to mention to finalize is with the following issue. I described attacks and I described risk. I didn't talk. I talked neither about detection nor about remediation, which are the most important parts of this game. And this is what we do in Lumini, and I will be more than glad to talk with you about it. And that's it.